SwayamPrabha. Digital India. Educated India.
Good morning. I'll solve a problem here on axial flow turbine. The statement of the problem is a small axial flow gas turbine with equal stage inlet and outlet velocities has the following design data based on the mean diameter. What are the data are given as inlet stagnation temperature T01 is 1100 Kelvin. Inlet stagnation pressure P01 is 350 kilopascal. Axial flow velocity can be taken constant throughout the stage. CZ as 260 meter per second. Mass flow M is 18 kg per second. Blade speed U being 350 meter per second. Nozzle exit angle alpha 2 is 60 degree. Gas stage exit angle alpha 3 is 12 degree. We need to calculate the rotor blade gas angle, that is beta 2 and beta 3, the degree of reaction, the blade loading coefficient, power output, and the nozzle throat area required. If the throat is situated at the nozzle outlet where the nozzle loss coefficient is given as 0.05. Let me solve the problem. I've indicated here a reaction turbine stage where a row of nozzle is presented here, followed by a row of rotor blades. And the blade speed is U. Now C1 be the inlet absolute velocity that makes an angle alpha 1 with the Z axis, and C3 be the exit velocity from the stage that makes an angle alpha 3. Now state point 1 indicates the condition of flow at inlet to the stage. Similarly, state point 2 indicates the exit from the nozzle, and state point 3 indicates the exit from the stage. Furthermore, C2 be the absolute velocity that makes an angle alpha 2 with the z-axis, and with respect to the rotor, W2 be the inlet velocity and W3 be the exit velocity that makes an angle beta 2 and beta 3 with respect to z-axis. Z being the axial direction and theta be the radial direction. Now, given C1 is equal to C3 and CZ remains constant within the stage. Let me draw the velocity triangle. U be the blade speed, right? First, let me draw the inlet velocity triangle to the rotor. So W1 plus U would result in C1. So here it will be W2. So this is W2, W2 and U would give you C2. This is W2 and this is C2. And W2 makes an angle beta 2 with respect to Z axis, while C2 makes an angle alpha 2 with the Z axis. So this is the inlet velocity to the rotor. Let me draw the exit velocity triangle with another color. So this is W2 plus U and this is C2. W2 makes an angle beta 2. This is, I'm very sorry, this is W3 exit velocity triangle. W3 plus U would result in C3. W3 makes an angle beta 3 with respect to Z axis, and C3 will makes an angle alpha 3 with the Z axis. So this is velocity triangle. So again, W2 plus U results in C2, and similarly W3 and U will give you C3. Now here W3 obviously would not be equal to W2 because of acceleration of flow within the rotor. Now what are the quantities given? Now let me put a line here. Okay, what are the quantities given? T01 is equal to 1100 Kelvin. P01 is equal to 350 pascals, kilopascal. CZ axial velocity is given as 260 meter per second. U blade speed as 350 meter per second. Alpha 2 60 degree. Alpha 3 is equal to 12 degree. What are the quantities that you'll have to calculate? We'll have to calculate beta 2 and beta 3. Then we'll have to calculate R, degree of reaction, Xi, blade loading capacity, and work output W. And finally, A2, cross-sectional area of the nozzle at exit. So these are the quantities we'll have to evaluate. Now, from the inlet velocity triangle, what we have got? I can write C theta 2 is equal to Cz into tan alpha 2. So C theta 2 is equal to Cz into tan alpha 2. I know the value of Cz. And also I know the value of alpha 2, Cz is equal to 260 meter per second, alpha 2 is equal to 60 degree. If you evaluate, you will get 450.3 meter per second. Similarly, from exit velocity triangle, right? Exit velocity triangle, what I'll get? I'll get C theta 3 is equal to Cz into tan alpha 3. I know the value of tan alpha 3. Alpha 3 is equal to 12 degree. So this is equal to 260 into tan 12 degree. If you do the calculation, you will get 55.26 meter per second. Thus, here I have calculated I have drawn the velocity triangle, and from inlet velocity triangle I have evaluated C theta 2, and from exit velocity triangle I have evaluated C theta 3. Hence, from the inlet velocity triangle, I can write W theta 2 is equal to C theta 2 minus U. C theta 2 I have evaluated as 450.3 and U is given as 350 meter per second. Thus W theta 2 I have got as 100.3 meter per second. After evaluating W theta 2, I can calculate for beta 2, that is inlet blade angle, as tan inverse W theta 2 divided by Cz. Now thus it would be tan inverse W theta 2 I have evaluated as 100.3, so this will be 100.3. Value of Cz is given as 260. Thus beta 2 I have evaluated as 21.1 degree. Please, you are requested to check the numerical values. Similarly, I can calculate beta 3. So I have projected W theta 3 as from exit velocity triangle U plus C theta 3, that is 350 plus C theta 3 I have evaluated as 55.26. Thus I have got, this is 405.3 meter per second. After that I can evaluate beta 3. So hence beta 3 would be tan inverse as before W theta C by CZ. So this is tan inverse. What is the value of W theta 3? That is 405.3. What is the value of CZ? 260. This I have got as 57.3 degree. Thus, I've evaluated beta 2 as 21.1 degree and beta 3 as 57.3 degree, which have been asked for. So the first part of our problem is done. Now I'll proceed further. I'll go to the second part of the solution. We know now our degree of reaction is equal to minus half of 5 into tan beta 2 plus tan beta 3. This is the expression that I have derived earlier. Now, considering the sign convention, as per the sign convention, beta 3 is negative. So if you consider the sign convention, the R can be expressed as half phi into tan beta 3 minus tan beta 2. Now let's put the value. The phi, the flow coefficient, is equal to Cz by U. I know the value of Cz and I also know the value of U. So this would be equal to half. Value of Cz is 260. U is 350 meter per second. Beta 3 and beta 2 I have evaluated. So this is beta 3 I have evaluated as 57.3 degree and beta 2 as 21.1 degree. After evaluating, I have got the value of R as 0.433. Thus, I have calculated the degree of reaction as 0.433. Now again, blade loading capacity Xi can be expressed as phi flow coefficient into tan beta 2 minus tan beta 3. Considering sign convention, as I told before, beta 3 is negative, so Xi would be equal to phi into tan beta 2 plus and beta 3. Since beta 3 is negative, so this would be equal to 260 divided by 350, 10, 21.1 degree plus 10, 57.3 degree. If you evaluate, you will get xi is equal to 1.44. So I have evaluated now the value of xi blade loading capacity as 1.44. Now power output would be W is equal to M mass flow rate blade speed into C theta 2 plus C theta 3 following velocity triangle. So I know all the values. M is given at 18 kg per second, U is 350, value of C theta 2 is 450.3 and C theta 3 I have evaluated as 55.26. So if you do all these things, it would be 3181.5 kilowatt. So the power output is 3181.5 kilowatt. So this is the part B I have completed now. Now let's go to the part C. That is, I'll have to evaluate now the exit flow area of the nozzle. Now again from velocity triangle, I can write C2 who's equal to Cz into sec alpha 2. This is the inlet velocity triangle. So I know Cz is 260 meter per second and alpha 2 is 60 degree. If we do that, C2 would be equal to, after calculation, 520 meter per second. We can define the nozzle efficiency as zeta n is equal to H2 minus H2S, that is, this is H2 actual enthalpy at the end of the nozzle, and H2S be the isentropic enthalpy at the end of the nozzle. So zeta n can be defined as H2 minus 2s. I have indicated both the point in HS diagram. This is HS diagram. Divided by half C2 square. This has been not nice flies. So this can be written as Cp into T2 minus T2s divided by half C2 square, or I can write T2 minus T2s actual and isentropic temperature at the end of the nozzle is equal to 0.5 to C2 square into zeta n divided by Cp. Put all the values, that is 0.5. C2 I have evaluated as 520. Here, look, 520, and zeta n as given as 0.05 divided by 1148. If you evaluate, you will get T2 minus T2s as 5.89 Kelvin. Please check the calculations. Now let us proceed further. For the nozzle I can write T02 is equal to T01. That means total temperature at the exit of the nozzle is equal to that of the inlet. Hence from here I can write T2 is equal to T02 minus C2 square divided by twice Cp, as T02 equal to T01, I can write 1100 minus C2 I have calculated as 520 divided by twice into 1148. After evaluating, I got T2 as 982 Kelvin. After evaluating T2, I can calculate T2s from the earlier equation as T2 minus 5.89. I have evaluated T2 as 982 Kelvin minus 5.89. So T2s have got as 976.1. Now I can say, using isentropic relation, P01 by P2 is equal to T01 divided by T2s to the power gamma by gamma minus 1. I know the value of both T01 and T2s. Thus I can write 1100. T2s I have evaluated as 976.1 to the power gamma by gamma minus 1 would be equal to 4. Thus the pressure ratio P01 by P2 would be equal to 1.61. Now I know the value of P01, so from here I can evaluate P2. Thus P2 would be equal to P01 is 350 divided by 1.61. If you do this, the value of P2 I have got 217 kilopascal. Now I got P2, that is exit nozzle pressure. So I can evaluate rho 2 since T2 is known to us. Let's go to the next slides. Thus, I can say rho 2 is equal to P2 divided by R into T2. Now the value of P2 is 217, which I have evaluated, into 10 to the power 3 Pascal. The value of R is 287. T2 I have calculated as 982. Thus I got rho 2 as 0.77 kg per meter cube. Now I know the flow rate through the stage is given as 18 kg per second. So I can write M is equal to, whether M means is a flow rate, I can write is also M dot equal to rho 2 A2 area at the exit, annulus area, and C2. Thus from here I can say A2 equal to M dot divided by rho 2 into C2. M dot is given as 18 kg per second. So this is 18. Rho 2 I have evaluated at 0.77. C2 I have evaluated as 520 meter per second. So if you calculate this, you will get 0.045. Please check the calculation. Meter square. Thus, I got A2 exit area of the nozzle as 0.045 meter square. With this, I have solved the problem. Thus, I have solved an illustrative problem on gas turbine, and I trust you'll be able to solve similar problem. Thank you for listening.